right, well, in this video, we're going to talk about the estimated standard error of the mean. Now, when do we estimate the standard error of the mean? Well, we do that when the population variance is not known. And in other words, that's most of the time. Most of the time, we do not know the variance in the population, so we have to estimate it. Okay, to give you some refresher, here's what the formula looks like for the standard error of the mean, right? And you can see here that in the numerator, we have the population standard deviation, and then it's divided by the square root of n, and that gives us the standard error of the mean. The problem is we usually don't have this. We usually don't have sigma, so we have to estimate it. That's going to require us to modify the formula just a little bit to create the estimated standard error of the mean. So you'll notice now we have s with the caret, which means that we're using the sample standard deviation to estimate the population standard deviation. Now keep in mind this estimate involves a correction, right? When we're trying to figure out the variance, we divide sums of squares by n minus 1, which is Besel's correction, and that's going to create an unbiased estimate of the population variance. So when you see this symbol, right, s with the caret on top, and it might be different in different textbooks, but when you see this symbol right here, what that means is you're using that corrected sample standard deviation to estimate the population standard deviation. But other than that, the formula is exactly the same. There's just some small changes to the notation in the numerator and then over here in the term that we're solving for. Okay, so let's do a sample problem and walk through it. Imagine you are a researcher interested in whether a new anti-inflammatory medication works to reduce the severity of COVID-19 symptoms in intensive care unit patients. Now, symptoms are rated 1 to 5, with a 5 indicating severe symptoms. The medication is given to 1,000 patients. You know the mean rating in untreated ICU patients is 4.25, but you do not know the variance in standard deviation. Now, in your sample of patients who received the medication, and that's an N, pretty big N of 1,000, the mean rating was 4.15, and the estimated population standard deviation, which I won't calculate here, I'll just give it to you, was 0.50. Okay, so we know from the problem that the patients who received the medication had lower severity of inflammatory symptoms, right? Their mean was 4.15. In the untreated population, it was 4.25. So we know that they have a little bit less. The question really is, you know, how far out in the left side of the sampling distribution would we locate a value of 4.15 for a sample mean? Okay, so what proportion of samples would have a mean of 4.15 or lower? Okay, so you can imagine a sampling distribution looking like this, right? The population mean, which we know is 4.25. And then the question becomes, where exactly does 4.15 show up on the left side of this distribution? How far into the tail is it? Okay, so really there's two steps to solving this problem, just like what we did with standard error of the mean. First, we have to calculate the estimated standard error of the mean, and then we have to calculate a z-score to locate the sample mean in the sampling distribution. Okay, so here's our formula for the estimated standard error of the mean, and we're going to plug in our data. We know that the estimated standard deviation was 0.50, and we also know that we had an n of 1,000. So the square root of 1,000 is, of course, 100. So 0.50 divided by 100 ends up being 0.005. The next thing we have to do then is to calculate the z-score. So to calculate the z-score, we just take the sample mean, right, which is right here, and then we subtract out the population mean, and then we plug in what we just solved for, which is the estimated standard error of the mean. Now in this case, it's going to be 4.15 minus 4.25 divided by 0.005. That's going to be negative 0.10 divided by 0.005. And that's going to translate into a z-score of negative 20. Okay, now think about that. What does that mean? Well, here's our sampling distribution, right? And what I'll do is I'll put in down here these standard scores, right? So we know that the mean in the sampling distribution in terms of z's for standard errors is going to be 0, right? Then there's -1 standard error, -2 standard errors, okay? And we ended up with -20 standard errors, which I can't even locate on my drawing, right? It's way out here, right? -20. If we were to just really increase this graph and go way, way, way out here, probably even off the screen, that's where we'd locate the sample mean, okay? So what does that mean? Well, what that tells us is that, you know, if we were to randomly draw a mean from the sampling distribution of 4.15, right, given that our n equals 1,000, okay, the probability associated with that would be at -20 z's. And we don't even have a table that gets that small. So exceedingly small probability that we would draw that value by chance. So in terms of decision making, and this is what's coming next, in terms of decision making, we have to make a decision. Should we give that medication to the patients or not? Well, the likelihood that we'd observe a sample mean, given a sample size this large, of 4.15, is exceedingly small just by chance or random. I mean, really, really small. So our conclusion would be, well, if it's not due to chance, right, then it's probably due to the efficacy of the medication. Okay, and that's generally where we're going in terms of understanding how to make decisions using statistics, right? Because ultimately we want to make good decisions. We want to make better decisions. What we're missing at this point is a rule, right, for telling us when the data from the sample looks so different from the population that we think maybe an intervention, for example, had an effect. We need to have some kind of rule for doing that. And we're going to be talking about how to make decisions involving what's called the null hypothesis. And that's coming down the road here very shortly in terms of our understanding of statistics. Right now, we have no formal rule, right, to make our decision. Okay, so big picture, when we do not know the population variance, we have to estimate it from sample data. Right? We're going to calculate the estimated standard error of the mean rather than the standard error of the mean. And just as an aside, a lot of times in statistics packages, they're still going to just call it standard error of the mean or SEM in the printouts and the output, even though it's really an estimate. And it has a similar interpretation to the standard error of the mean. And really the only difference in terms of decision making involves smaller samples, you know, when you get to n below 30 or so. But other than that, the calculations between standard error of the mean and the estimated standard error of the mean, once you get over 30, are going to be pretty similar in their conclusions. Okay, so that's going to do it. I hope you enjoyed this video, and we're going to be moving our way more and more toward hypothesis testing. Okay, next thing we're going to do is talk a little bit about the shape of the sampling distribution. I'll see you there.